Hello, welcome to my Physics Lab 5 on the falling slinky. So the system in this problem is a slinky that he's dropping. The surroundings are just Earth, and in this video the slinky is stretched until it's at its equilibrium length with the Earth pulling on it, and then it's dropped, and the focus is on where the bottom of the slinky is and when it drops. So we'll use the tracker software to observe the motion of the bottom of the slinky during the video, and then compare this to a GlowScript computational model. The goal is to test if in the simplified model we'll have the same findings of the still bottom end of the slinky, in that when he initially drops it, the top has to hit the bottom for it to go. And the result is that we did. The fundamental principles here are Newton's second law, which gives us the velocity update and position update formula here, as well as the energy principle using the force of the slinky, which is just thought of as the tension force, equaling the force of gravity. We also use the drag force for when the slinky is eventually in motion, with this proportionality constant that we changed to line up with the observed model. So in the observed data, I use this guy's height to calibrate, and then I found the mass of the slinky in an article talking about this video in the problem, which had it as 0.218. And the initial position of the bottom is 0 because it's right at the start, and the initial velocity is 0 also because it is at rest. So this is kind of the same, it's just the initialization of the code. The only thing important here is that what I found lined up best was a drag coefficient of 88. It was the closest to the observed data. So here we have two while loops, one while time is under 5.1 seconds and one with time under 8.2. So this is when the slinky is dropped and the bottom is still being pulled by the tension of the top. In the video, they talk about where this is when the bottom doesn't know what's happening above it, so it doesn't know to drop. But in this, it's still, so there's no drag, and the force is just that of the tension pulling it up, whether the slinky is compressed or stretched or not. And then this bottom one takes into account drag because it is in motion, and this is just kind of when it's falling. So we use Newton's second law. So the results we got line up pretty well here. You can see the observed data is a bit more jumpy, just because in the tracking data I was kind of moving around a little bit inaccurately compared to the computational model. The computational model does drop a bit faster, so there are some forces that could have been here resulting in some error, like wind or anything that would keep the slinky from falling as fast or faster, just depending on the conditions that we can't really tell to input into the model. So why does the bottom of the slinky remain stationary when it's dropped? It remains stationary because the tension force of the slinky is the same during the initial time of the drop, because basically the tension force equals out the weight force, and it doesn't matter where it is in its compression. He talks about kind of a wave of information being sent down the slinky, but it's really the point mass at the bottom doesn't know the length of the tension vector, basically just the magnitude, and until it like collapses into one point mass, it won't drop. So at what mass would the slinky move? So like say you added 100 kilograms to the bottom of the slinky, it seems like those 100 kilograms would drop first, and it just depends on the weight relative to the spring force constant, because at a certain point it is going to drop because the tension above wouldn't be enough to hold it. But given that it's held at rest, as long as it's not like about to break, it will kind of follow these same parameters. Thank you.